Previously, we had taken a look at Newton's first and second laws of motion, introduced some different forces, and looked at how those forces could affect the motion of objects. I'd like to return now to Newton's third law of motion to complete his laws of motion. And like I did with the first and second laws, I will go ahead and quote from an English translation of what he wrote in Latin in the Principia. To every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. Okay, so what does all that mean? So what Newton is saying here is, first off, that all physical interactions are mutual. In fact, between additions, after the first few additions, Newton actually added the bit after the semicolon in later editions of the Principia because readers were not quite following it. It's not a cause and effect relationship. It's not like one thing happens and then as a response the other happens. And that's probably because he actually chose the words action and reaction, which makes it sound like there's a causation. That's why later Newton clarified it by saying the mutual actions of the two bodies. So this means that both of them are interacting in Newton's model with each other at once. This also means that both players in the interaction feel the same force feel the same force in opposite directions. So what do we mean by that? It means, say, if I was to push on, let's say, a shopping cart with 5 newtons of force, the shopping cart pushes back on me with exactly 5 newtons of force. No more, no less. And this will always be the case. And if I push the shopping cart, say, to the right, the shopping cart will push me to the left. I already touched on this a bit when we were saying that the interactions are mutual. It's also true that all interactions are simultaneous. Meaning that they happen at the same time. So when I push on the shopping cart, there's no delay in the shopping cart pushing on me. And this would be because me pushing on the shopping cart is an example of the normal force. It's the normal force between my hand and the handle on the cart. And so as I push on the shopping cart, what happens is I'll deform the handle and it'll try to return back to its original shape, attempting to push my hand out of the way. But at the same time, the shopping cart is deforming my own hand, and it's trying to return back to its original shape, trying to push the cart out of the way. So there's no time lag here at all. The two interactions happen at the same time. And also, to be a third law pair, Newton is also saying that all the interactions are of the same type. So, for instance, the shopping cart example that I just gave, the two forces in question were both normal forces. The normal force of my hand on the handle, the normal force of the handle on my hand. It could be something else. It could, for instance, be gravity. The earth is pulling down on me, and I'm pulling up on the Earth, and those are both gravitational forces. So, to be a third law pair, the interactions are mutual, it's always the same amount, they're simultaneous, and they're of the same type. So, to make this kind of more concrete, let's take a look at some examples of third law pairs. And I prefer the term third law pair. However, a lot of books will call them action-reaction pairs. They go by either name. I prefer third law because, again, I want to emphasize that these interactions are simultaneous. So let's just take a look at your physics book lying on your desk. So here is a desk, probably more like a table, really. And there's your physics book. All right, let's go ahead and analyze the forces acting on your physics book. So we'll start by drawing a force identification diagram. So now what we've got here is we have a normal force acting on it. And I am going to be super duper careful in this and say that this is the normal force of the table pushing on the book, just so we have some clarity here. And then if we go and look at long-range forces, it would be a force of gravity. And so again, who's the agent here? The agent here would be the Earth, and that would be acting on the book. So I'll go ahead and write it like that. Now, if we go ahead and draw a free body diagram for this, what are we going to get? We will have our normal force up. So this will be the normal force of the table acting on our book. And we will have the force of gravity from the Earth acting on the book, pointing down. So these are equal and opposite. So my first question to you is this a third law pair? Well, the answer is no. No, it's not. These are two forces that just happen to be equal and opposite. How do we know they're not a third law pair? Well, first off, both forces are acting on the same object. In order to be a third law pair, the forces have to act on different players. So it already flunks the third law test from that point of view. But gravity and the normal force are also different kinds of forces, so it flunks the third law test from that point of view as well. But that is our free body diagram for the book. Now, this sort of thing happens often enough where you get two forces that just happen to be equal and opposite acting on the same object, that I give this kind of force pair the name second law pair. And these are just two forces that just happen to be equal and opposite acting on the same object because the requirements of the second law, in this case, since the book isn't accelerating, the net force has to add up to zero. If there's only two forces, the only way you can do that is to have two forces that are equal magnitude, opposite direction. But they are not a third law pair. So let's go and find the third law pair, the forces that are third law pairs to this. All right, so let me go ahead and draw another table and book here. So we'll have a table again. And there's a floor. Yeah, I can spell today. There we go, and there's our physics book. All right, so now let's go analyze the table. So again, we will draw a force identification diagram for our table. And we see it cuts through two surfaces. So we've got two sets of contact forces. So cutting through the book, what do we have? Well, we have a normal force acting from the book. So we'll say this is the normal force of the book acting on the table. So when you think about it, if we look here, if the table weren't here, the book would want to fall through the table, would want to fall down. But the table is here. So how does the book know how to come to a stop? Well, the answer is it doesn't. As it tries to fall through the table, it actually changes the shape of the table a bit. The table will give. And the table's trying to return back to its original shape, and so it's pushing up on the book. But since the table's pushing up on the book and the book wants to fall down, what does that mean? That means the book gets compressed a little bit. And so the book's trying to return back to its original shape as well, trying to push the table out of the way. So that's the normal force of the book acting on the table. And by the same token, we will also have a normal force of the earth on the table as well. So I'm just going to call the floor the earth. We can pretend this is in a basement or something like that. So I don't want to think about transferring loads through a building or anything like that. But we can say this is the normal force of the earth acting on the table here, where it cuts through the earth. Do we have any long-range forces? Sure we do. We have the force of gravity acting on the table, and the responsible player for that is the earth. Okay, so we can go ahead and draw a free body diagram now for our table. So what will we have? Well, we have the normal force, acting down here. We will have the normal force of the book on the table. Now, this force here and this force here, those are an action-reaction pair. And the way I mark action, or a third law pair, and the way I mark third law pairs is I will put a slash through them. For the first third law pair I find, I'll put a single slash, then double slash, then triple slash, and I'll switch to doing X's, 1, 2, and 3 X's. You'll see other people and some textbooks will instead draw dotted lines connecting the two arrows, but in any event, however you want to do it, this marks a third law pair. So I use the slashes just because it makes the diagram less cluttered. All right, what else do we have acting on it? Well, we will have the normal force of the earth on the table acting up on it, and we will have a force of gravity due to the earth acting on the table. All right, so we found one of the third law pairs to this normal force of the table in the book, but we haven't found the other one yet. And the other one we can get from the clue of who's doing the interacting here is the earth interacting with the book. So now what I'm going to need to do is do a free body diagram, do a force identification diagram for the earth itself. And sitting on the earth is a table that has a book on it. All right, so let's do our force identification diagram. We will ignore the force of gravity from the sun acting on the earth and from the supermassive black hole at the center of the Milky Way galaxy and so forth, just because we got to bring this sleigh ride to an end somewhere. But draw a circle around the earth, we see that it cuts through the table legs. So we have a contact force. It's the normal force of the table acting on the earth. Do we have any long-range forces? The answer is yes, we do, actually. We have the long-range force of gravity from the table pulling on the earth, and also a force of gravity from the book pulling on the earth. So if I were to go ahead and draw a free body diagram for the Earth, what would we have? Well, we would have the normal force of the table on the Earth trying to push it down. We will have two forces of gravity trying to pull it up. We will have the force of gravity from the book on the Earth trying to pull it up, and the force of gravity from the table on the Earth trying to pull it up as well. All right, so that will let us identify our other third law pairs. So here is the normal force of gravity from the Earth on the book. That's a third law pair. The normal force of the Earth, the force of gravity of the table on the Earth is a third law pair to the Earth on the table. And the normal force of the Earth on the table is a third law pair with the normal force of the table on the Earth. And now we can see that everybody's got a buddy. The normal force of the table on the book had the normal force of the book on the table. The force of gravity from the Earth on the book had the force of gravity from the book on the Earth trying to pull it up. The force of gravity of the Earth pulling on the table has the force of gravity of the table on the Earth, again trying to pull the Earth up. There is a normal force of the Earth on the table trying to keep the table from crashing through it, and likewise there's a normal force of the table on the Earth that's keeping the Earth from flying through the table. Now that may seem a little odd at first, to say that we've got these forces of gravity here, and we totally do. The thing is, we don't usually really notice them, and that's because, or we don't really worry about them too much, and that's because they're of the same magnitude. So let's say your physics book, has a mass of, let's say, a kilogram or so. That would be, round numbers, a force of gravity of about 10 newtons. Now, 10 newtons has a pretty substantial effect on a book of a mass of 1 kilogram. However, when you're talking a mass as ridiculously big as the Earth, that same 10 Newton force isn't going to accelerate the Earth worth a hill of beans, if that were the only force acting on the Earth. Now, of course, we've got the table pushing down on the Earth to keep that from happening. But this is indeed what happens. There is indeed a force of gravity trying to pull the book up, but the table legs are compressed, because remember, the table's trying to fall through the Earth. The table legs got compressed and it's trying to, so as a result, those table legs want to return back to their original shape. They're trying to push the Earth out of the way. So as a result, it tries to push the Earth down. This winds up having the effect of canceling out the gravitational influence both of the book on the Earth and the table on the Earth. So even though either of these would be such a small force that you literally wouldn't even notice the Earth accelerating if they're the only force, we do have the normal force acting on the Earth as well to keep the Earth from moving at all. Okay. Let's go take a look at another example. Let's say that we're looking at a tug of war. So let's say we'll have a tug of war across a river. There you go. You now know it's a river because I labeled it. Any tug of war has to have a winner and a loser. There. So there's our winner. There's our loser. And they are pulling on a rope like so. So here's the thing. Since in tug of war, basically nothing's moving, the force of each player, or the rope basically isn't moving to worry about. The force of each player on the rope is basically zero. And in fact, let's go ahead and make the rope massless, or not is zero, but is the same. And in fact, we can even go ahead and say the rope is massless to make it this a little easier to think about, in which case definitely the two players are pulling on each other the same. And in any event, so what that means is that the rope is exerting a force due to tension on each player that's the same. So if the forces are the same, basically the rope is tugging on the on the player, and the player's tugging on the earth equally hard. So the player's tugging on the rope equally hard, and the loser's tugging on the rope equally hard with the rope. How is it that you ever have a winner and a loser? Think about that for a second, and we'll get back. All right. So for this, let's go ahead and take a look at the free body diagram for our winner. So we will have a force of gravity pulling down on our winner. And we will have a normal force from the earth pushing up on our winner. And those two are a second law pair. They'll cancel out. All right. Are there any other forces acting? Sure there are. If I draw a circle around the winner, I can see that we go through the rope. So that means there has to be a force due to tension in the rope. Anything else? Sure. Let me draw the shoes, because the shoes are really going to matter here. When the shoes are in contact with the earth, and so we will have a force due to static friction. There we go. Of the earth on the winner. So we end up with a net force to the left will be what I contend. So I'll contend that this tension is less than the force of static friction on the winner. Let's go look at the loser. Same deal. There'll be a normal force on the loser and a force of gravity on the loser. Again, they cancel by the second law. There will be a force due to tension acting on the loser. And these two tensions are a third law pair. And then finally, there'll be a force of static friction acting on the loser. So this is again from the earth acting on the loser, trying to move the loser to the right. So again, we end up having a net force to the left, and so the loser is going to get dunked in the river, and the winner is happy because they're going to stay dry. All right, so how is it that the, whoops, I did not mean to put those slashes through there just yet. So how is it that the earth knows to push on the winner harder than it's pushing on the loser? Now there is where the efforts of the winner and loser actually come into play. Let's draw a free body diagram for the earth, and I'm going to skip a lot of forces, but there are two that I really want to think about. There will be the force of static friction from the winner acting on the earth, and similarly, there will be a force of static friction of the loser whoops, acting on the Earth. This is a third law pair, and that's a third law pair. Now here, what's happening is the winner, as they're digging in, their feet are trying to push the Earth off to the right. In fact, the soles of the shoes will get a bit of a shear to them and will be trying to return back to their original shape in order to push the Earth over to the right. And in so doing, they'll deform this patch of dirt right here under the winner, and that patch of Earth will try to return back to its original shape. So the Earth's been kind of pushed up, twisted a little bit rightward. It's trying to return back to its original shape, pushing the winner over to the left. By the way, you can actually see this sort of deformation actually happening. If you look at a road near a stop sign or a traffic light, if you look right near the stop lines, you'll notice that if the road is a little older, you'll start to see divots kind of dug into the asphalt. And that is because as the tire starts to rotate, it's pushing the asphalt backwards, and the asphalt trying to return back to its original shape is what pushes the car forwards. Now with time, the asphalt fatigues, and you wind up building those divots behind the stop line. And exactly the same thing is happening in miniature here. The foot of the winner is pushing off this way, trying to force the Earth to move to the right and deforming the Earth. And as a result, the Earth, trying to return back to its original shape, is pushing the winner to the left harder than the rope is pulling the winner to the right. Same thing is happening here at the loser. The loser is trying to push the Earth to the left. However, they're not pushing the Earth to the left as hard as the winner is pushing the Earth to the right. Now, for however hard the loser pushes the Earth to the left, the Earth will push back on the loser to the right. Again, same deal. We're changing the shape of the Earth right here, kind of bending the Earth over like this a little bit to have it try to return back to its original shape, pushing the loser along for the ride. But here, because the loser isn't pushing on the Earth as hard with their feet as the winner is, the force that the loser's exerting on the Earth is less than the force due to tension in the rope, and so the loser ends up accelerating out to the left. And so, as a result, the winner will accelerate to the left, then the loser accelerates to the left. And to be clear, the Earth is accelerating to the right. But again, not by a whole heck of a lot, because since, remember, Newton's second law says the acceleration is equal to the net force exerted on an object over the mass of the Earth is so absurdly large that we basically don't notice the teeny tiny little bit that it gets accelerated during this process. Okay. I'd like to finish up this video by doing an example to show how we can use the third law sometimes to identify not so obvious directions that some forces may have. So this example here, I'm going to imagine that this is going to be a horrible pickup truck, but just roll with it. It's not going to be any better. It's not going to get any better with me trying to draw it better. Trust me on this. All right, that is a terrible pickup truck. And let's go ahead and say that there is a crate in the pickup truck. And we know that the crate is not slipping. We know that the pickup truck and the crate in it are accelerating to the right, let's say 2 meters per second squared, doesn't matter, just making up a number. What I'm interested in is drawing free body diagrams for the truck and the crate here. So again, so I guess I should probably draw it in a road here as well. So again, what we can do is we can draw a force identification diagram for our crate. And we see that it cuts through the bed of the truck. So that's a surface. So that means we have both a normal force, and I'll label this truck on crate, and a force of static friction, truck on crate. And then long range, we have force of gravity acting on the crate. Okay. And I can do the same thing. I'm going to ignore rolling friction here, even though I probably shouldn't, and I'm going to ignore air resistance, even though I probably shouldn't, just because I don't want to get lost in the weeds here. But if I draw a force identification diagram for the truck, what do I see? I see, first off, I can cut through the earth, so there's a normal force of the earth on the truck. And correspondingly, there's also a force of static friction of the earth on the truck. Oops. Earth on truck. But look here. The circle also cuts through the crate. That means that there's also a normal force of the crate on the truck and a force of static friction of the crate on the truck, which makes sense. This is by the third law. And then we have to ask, are there any long-range forces? And we say, sure, of course there are. It's the long-range force of gravity on the truck. All right. So now we can start to draw the free body diagrams. And since we've only got 3 forces acting on the crate, let's start there. We've got 5 forces acting on the truck, plus the ones I ignored. So I think the crate will be easier to start with. So the immediate win is in the vertical direction, where we know that we have a normal force of the truck acting on the crate. And I know that we have a force of gravity. Oops. Acting on the crate. And these are equal in magnitude by the second law, because it's not levitating off the truck and it's not crashing through it. But so if we look at our force identification diagram, there's also a force of static friction. And we need to ask ourselves, okay, which way does it point? It's got to be parallel to the surface, so it's either right or left. And it's got to be to the right, right? Because in order for the crate to accelerate to the right, there has to be an unbalanced force to the right. And there's literally only one force left. So the only force it could possibly be is static friction of the truck on the crate. Now that may seem a little counterintuitive, but this will actually be a little easier. It's easier to find the direction of this than it is to think about it when it's happening with the truck, at least for me. So let's go ahead and look at the truck now. So same deal here now. Let's go ahead and put in the low-hanging fruit. We have a force of gravity acting on the truck, right? And we have a normal force of the earth on the truck. But we also have a normal force of the truck on the crate, of the crate on the truck. We had identified it with the force identification diagram, and we can get the direction via the third law. Since the corresponding, I'll just draw it off to the side like that. So normal force of crate on truck. That's a third law pair there. So since I found this one, I know here that the crate has to be pushing down on the truck, which is what allowed me to draw this normal force bigger than gravity in this case, because I already knew where this was going. And we also know the weird thing that it's the force of static friction that makes vehicles go forward. So this force of static friction of the earth on the truck pointing forward makes sense. But remember, we also had a force of static friction of the crate on the truck, and that points backwards. And we again get that because since we worked out that the only way it could point on the crate was forward in order to make it accelerate forward by the second law, by the third law, that means it has to point backward on the truck. So that's what I mean, that sometimes the third law makes it easier to find the directions of forces that aren't so obvious. You can go and look at the other player, think about which way the force has to be pointing there, and then the third law, then you can just hold your nose and use the third law to get the correct direction on the less obvious player. By the way, there's another way you can think about this, if it helps for why it should make sense that the force of static friction of the truck on the crate is forwards here. So as this is accelerating, let's imagine we start from a stop. The truck will accelerate forward. By Newton's first law, the crate would want to just literally hang there in space, right? So what's going to happen? The crate trying to hang there in space is going to interact with this surface that's pulling forward. That's going to distort both surfaces. It's going to curve this surface this way, and it's going to curve this surface towards the back. Both of them are going to want to return back to their original shape. This surface being curved toward the back will want to snap forward, pulling the crate forward with the truck. This surface being bent forward will want to snap backward, pulling the truck, trying to pull the truck backwards. So that's another way that you can think about it. And since physics must be consistent, either way to think about it will give you the same answer. Alrighty then, in the next video we'll do a few more applications of Newton's third law, mostly looking at a trick that I like to call cleverly choosing your free bodies. Catch you in the next video.